Hey, welcome back to chemistry. And so with this presentation, I want to talk about something called electron configuration, which tells you that for any particular element, which orbitals of that element have electrons. For example, does the element let's say it's vanadium. Will its 1s orbital have electrons? Will its 3d orbital have electrons? Will its 2p orbital will have electrons? So you have to figure out for any particular element which orbitals are filled up with electrons. And so I sort of need to teach you how to do that. And so the first thing you need to learn is you have to understand the order of the orbitals that are filled by electrons. And so the basic rule here is remember that orbitals are filled up from lowest energy to highest energy. So the first electrons which go into an atom will go into the lowest energy orbital, say like the 1s orbital is the lowest energy orbital. And then once the 1s orbital is filled, then the next higher energy orbital up, the 2s is filled, and then the 2p and the 3s and the 3p and so on. Now, here's the thing. You can memorize that order of orbitals if you want to, or there's a quick way to figure out the order because it may not be so clear sometimes what the order of the orbitals is. And so the way you figure out the order of the orbitals is using something called the diagonal rule. So I think the best thing for me to do is just to sort of draw out the diagonal rule on this board here, and then that will tell us what the order of orbitals is that electrons fill from lowest energy to highest energy. So what you do is you list out all the orbitals that an element can have. So for example, all elements can have a 1s orbital. So a question I ask is, can an element have a 1p orbital? And the answer is no. And so you might remember when you're dealing with the first energy level, the only sublevel that exists is the s sublevel. There is no p sublevel. So I do not write 1p here. Now, in the second energy level, there is a 2s sublevel. There's also a 2p sublevel, but is there a 2d sublevel? And I think you know by now, when you're in the second energy level, the only two sublevels that are there are the s sublevel and the p sublevel. There is no d sublevel. Third energy level, it's 3s, 3p, 3d. There's no 3f. 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. Now you might have learned somewhere that after the f sublevel, you might have another higher energy sublevel called the G sublevel. So the question is, do we write it in 5G? Now you could if you want to. I usually leave it out. I don't go any further than F, and the reason is if you look at the periodic table, I think you have now up to what? I don't know, about 118 electrons that can fill orbitals. And so I think by the time you get up to the 5G, that 5G will not pick up those highest energy level electrons of the 118 that are there. So I don't bother writing 5G. So I next write 6s, 6p, 6d, 6f, 7s, 7p, 7d, 7f. And so that should be enough. Okay. So to figure out the order of the orbitals, what you have to do is draw diagonal lines to this sort of chart here. And so the first diagonal line only cuts through the 1s orbital like this, and so I'm going to put a 1 here for that. The second diagonal line only cuts through the 2s like this. The third diagonal line cuts through the 2p and 3s. The fourth diagonal line cuts through the 3p and 4s. The fifth diagonal line cuts through the 3d, 4p, and 5s, and so on, 4d, 5p, 6s, for the sixth diagonal line, and then 4f, 5d, 6p, 7s. So you can write out the order of the orbitals determined by going through these diagonals in sequential order and just writing out the orbitals that they hit in order. So the first diagonal line hits 1s. So the first orbital that is filled is the 1s orbital for any atom, and that will have the lowest energy. So we're done with the first diagonal. Going down to the second diagonal, it hits only 2s. So that is the next orbital up in terms of energy. Third diagonal is 2p3s. and then go to the fourth diagonal, it's 3p, and then notice it's not 3d. You go to the fourth diagonal, it's 3p 4s. So 4s actually has a little bit lower energy than 3d. So it's 3d 4s, or excuse me, 3p 4s. 3p 4s. Okay, now we go to the fifth diagonal. We have 3d 4p 5s. So it's 3d 4p 5s, and then the sixth diagonal, which is 4d 5p 6s. So it's 4d, there we go, 5p 6s. And so you can keep going on with this, but again, sort of to know that this order, which I'm writing out from left to right, is the order of orbitals in terms of energy and also the order in which they are filled. So here again, on the left side, the 1s orbital is filled first, then this 2s orbital, then the 2p, 3s, 3p, 4s, etc. Okay, so we have that order there. I might leave that there just for a second. So I'm just going to erase this chart here. Now, I think it's kind of a good idea to have in your mind sort of a sense of what the energy diagram of these orbitals on that diagram would look like. So what I'm going to do is I'm going to draw an axis here. This is going to be a y-axis, and I'm going to put energy on the y-axis. And I'm going to indicate on this diagram where the orbitals reside on this energy diagram. And so the lowest energy orbital on this axis is going to be as low as I can possibly place it. So I'm going to put it here for now. So I'm going to put 1s here. So to indicate that I have an orbital, I have a line here. How about the 2s orbital? Well, it's higher in energy, so I'm going to put that a little bit further up here. So that'll be the next orbital that is filled. And then next is 2p. That's going to have a little higher energy than 2s. I could put the 2p right above the 2s, but just, so it's a little bit clear, I'm just going to shove it over to the right here. So I'm going to write a 2p orbital here, but here's the thing. You might recall that the s sublevels of the 1 and the second energy level only have one orbital, so that's why I drew one line there. But a p sublevel, doesn't matter what energy level belongs to, it could be the second, the third, fourth, whatever. A p sublevel has 3 orbitals, and so what I'm going to do is I'm going to draw 3 lines here. So 1, 2, 3 are the 3 orbitals for the 2p sublevel. Okay, so what's the next orbital up? So this is the third energy level s sublevel, so that's 1 orbital. So I'm going to put this here. So one of the things I want you to notice as I'm drawing in these orbitals, I'm kind of squeezing them closer and closer together, because that's what has been experimentally found, is that as you go further up in energy, the orbitals are not, or have less and less of an energy difference as you go up. So we have the 3s there. The next is the 3p. So a little bit higher energy than that. I'll put this in the p area here. There are 3 of them, orbitals, because it's p. Okay, so what's the next one is the 4s, which is a little bit higher than 3p. And then the next one up is the 3d. That actually has a little bit higher energy than 4s. So I'll just put that over there. So would I write out 3 lines for 3 orbitals for the 3d sublevel? No, because this is d sublevel, there are 5 orbitals, and so I have to draw out 5 lines. And so I'm just going to go a little higher than the 4s and draw out 5 lines. 1, 2, 3, 4, 5. And this is the 3D sublevel. And if you wanted to, you can go up further from there. Now, one thing I want you to notice is that when we have a sublevel with multiple orbitals, whether it be a p sublevel or a d sublevel, what I tried to do was each of these orbitals, I tried to put them on the same line, indicating that each of these orbitals in the sublevel have exactly the same energy. So when you have orbitals in a sublevel that have exactly the same energy, they are said to be degenerate orbitals. And so the word is degenerate, D-E-G-E-N-E-R-A-T. So also the 3D orbitals are degenerate orbitals because these 5 orbitals of the 3D sublevel have exactly the same energy. And so these would be degenerate orbitals as well. Okay. So what I'm going to do now is I'm going to carry out a bunch of electron configurations. And so I'm going to erase this briefly, and I'm going to make a new chart. Okay. So I'm going to write up here, in this corner here, I'm going to write element and electron number. Let me pop the slide over. So here is another picture of the energy levels for each of these sublevels. And so I want to go to here. I'll talk about what's on the slide in just a second. So back to this chart here that I'm drawing out is element electron number. The next thing I want to write is orbital notation. And then I want to write electron configuration notation. Then I'm going to write Qn for quantum numbers. Then I'm going to write something called Lewis dot. I'll explain what that means in a minute. And then I'm going to write the abbreviations P or D. Okay, so P means paramagnetic, and D means diamagnetic. Diamagnetic. Looks like I spelled it right. Amazing. Okay, so I'm going to put little lines here. Okay. All right. So as I'm going through the electron configurations for some of the elements with the fewest number of electrons, I'm going to be describing it as I go along, and I'll be using some vocabulary. And I'll try to define the vocabulary as I'm going through this. But if you want, you can sort of refer to the glossary I have on this board here. Okay, or on the slide there. Okay, so the first thing I want to do is consider the electron configuration of hydrogen, which has only one electron. So I have hydrogen here, and there's one electron, so I'll put parentheses 1e. So the question is, what orbital does this one electron of hydrogen go to? So in hydrogen, there are plenty of orbitals. There is the 1s, the 2s, the 2p, 3s, 3p. Which one does it go to? Well, what you know is that electrons go to the lowest energy orbitals that are available to them, and they fill those orbitals. And so the lowest energy orbital that's available to this single electron from hydrogen is a 1s orbital. So this single electron from hydrogen will go there. So to indicate we have a 1s orbital in hydrogen with a single electron, this is what I do, how I write this out in orbital notation. I draw a line in orbital notation to indicate the orbital, and then I write 1s here. And to indicate the electron, I draw a line with an upward arrow. So this is the correct orbital notation for hydrogen single electron. So there's also something called electron configuration notation. So this will also indicate that there is one electron in the 1s orbital of hydrogen, but I use numbers and letters and superscripts to indicate that. So we have one electron in the 1s, so I write 1s, and to indicate the number of electrons in that 1s orbital, I write a superscript 1 like this, and so this is the electron configuration notation for the hydrogen electron. Okay, so one thing you have to sort of continue to suffer through is figuring out what the quantum numbers are for this electron. So let's see if we can figure that out. So you might remember there are 4 quantum numbers, so I'm going to list them here. There is the quantum number n, which indicates the energy level that this electron is in. There's the quantum number L, which indicates the sublevel that this electron is in. There's a quantum number m sub L, which indicates any particular orbital of the sublevel that this electron may be in. And there's a quantum number called m sub s, which indicates the spin of this particular electron. Okay, so what are the values of these 4 quantum numbers for this electron of hydrogen? So n is just the energy level that this electron is in. So n for this electron is 1. How about L? L indicates the sublevel the electron is in, and here's a little bit of memorization. You might recall when L has the value of 0, what that indicates is that that electron, if L is 0, is in an S sublevel. If L has a value of 1, it's a P sublevel. It's a value of 2, it's a D sublevel. If it's a value of 3, it's an F sublevel. Okay. So here we have an electron in the S sublevel, so the value of L must be 0. the value of m sub L, you may recall, it can vary from plus L through 0 to negative L. So here, because L is equal to 0, m sub L is 0 to 0 to 0. It's plus 0 to 0 to negative 0, which is 0. So there's really only one orbital in the s sub level in the first energy level, and this orbital will have an m sub L of 0. Okay, so how about what the value of the spin quantum number is? And so it could either be plus 1/2 or negative 1/2. And so if we draw an upward arrow like this, by convention we say that this electron is spinning in a clockwise direction. And if that's the case, then we assign a quantum number to that kind of electron of plus 1/2. If it was spinning in the opposite direction, we would say it would be negative 1/2, but it's going up, so it's plus 1/2. Okay, a Lewis dot structure. Okay, this will become more important later, but I'll teach you how to draw out a Lewis dot structure. What this is a representation for a particular element, how many electrons there are in the highest energy level of that element, in which you can sort of figure out from these notations. So the first thing in a Lewis dot structure you write is the symbol of the element, which is H. Okay, and then you ask yourself this question: how many electrons are in the highest energy level of this element? So what is the highest energy level that electrons are in hydrogen? Well, there's only one electron, and its highest energy level is the only one that's there, and so that's the first energy level. And so there's one electron in the first energy level, which is the highest energy level that electron is occupying in hydrogen. And so therefore, since there's one electron there, we write one dot, and we put this dot next to the symbol. Okay, paramagnetic or diamagnetic. So let's talk about what makes an element as paramagnetic and what makes it as diamagnetic. So first off, what paramagnetism is that it suggests, or rather, if you have an element that is paramagnetic, what that means is it'll be attracted to magnets or magnetic fields. On the other hand, if you have an element that is diamagnetic, it will not be attracted to magnets or magnetic fields. In fact, it might be slightly repelled by them. So how do you determine whether an element is paramagnetic or diamagnetic? And the way you tell is by looking at the orbital notation for the element. An element is diamagnetic when all of its orbitals, every single one that has electrons, has a pair of electrons in them. On the other hand, an element is paramagnetic when it has at least one orbital with only one electron in it. Now, it could have more than one orbital with one electron. There may be two orbitals or three orbitals, each with one electron. Doesn't matter if you only have one or more. If there's an orbital there with just one electron in it, that makes that element attracted to magnets or magnetic fields, and so it's classified as paramagnetic. So hydrogen here has one electron in the one orbital that it occupies. It's not a pair here, it's just one. Therefore, it should be attracted to magnets. The hydrogen atom, at least, should be attracted to magnets, and so it's considered to be paramagnetic. Okay, so the next element we're going to talk about is helium. And this has two electrons. So what I'm going to do now is write out an incorrect configuration for helium to make a point. So this, what I'm writing is wrong. I'm going to erase in just a second. So we have the 1s orbital in helium, and it'll have two electrons. And so what I'm writing is wrong. I'm writing one arrow up, and I'm writing the second electron with its arrow up as well. This is wrong. And so why is it wrong? It's wrong for two reasons. One is that when you have a pair of electrons in an orbital, they must be spinning in opposite directions. So if you have one that is spinning clockwise, as indicated by an upward arrow, the other electron must be spinning counterclockwise. And so we would indicate that by flipping over this arrow and have it point downward. Now, there's another reason why this is wrong. So let's say we were to write the quantum numbers, the four quantum numbers for this electron on the left here, the one that's pointing up, or this one on the left. So n is 1, it would be this. N is 1, it's an s sublevel, so it's 0. There's only one orbital in the s sublevel, so the next quantum number is 0. And then this arrow here is pointing up, so it's a electron spinning clockwise, so it's going to be plus 1/2. So that would be the quantum numbers for that electron. Now this electron will have quantum numbers too, but look, it's in the same orbital as this first electron, and it's also spinning in the same direction. And so it will have exactly the same quantum numbers. Now there's a rule in quantum chemistry that says that whenever you're looking at electrons in an atom, no two electrons can have exactly the same four quantum numbers. They must have different quantum numbers. All you need is to vary one of the quantum numbers, and then that would be fine. So this cannot exist because both of these electrons have the exact same set of four quantum numbers. So this cannot possibly be true. So I'm going to erase this and draw the correct electron configuration of helium. So it's going to be 1s, and then the first electron is in the 1s orbital and spinning clockwise, and the next one must be spinning counterclockwise. So that is correct. So this is 1s2. And so now what we can do is write out electron configurations for these electrons. So for this first electron here, it's exactly the same it's exactly the same quantum numbers as this hydrogen's electrons because it's in the same orbital and it's also spinning clockwise. So it is also 1, 0, 0 plus 1/2. The quantum numbers of the next electron over, it's in the same orbital, so these first three quantum numbers, if it's in the same orbital, must be the same, but it's spinning in the opposite direction, it is negative 1/2. Now, what is the Lewis dot structure for helium, or notation for helium? So you write the elemental symbol, which is helium, and so we check the highest energy level of helium. We only have one energy level here that has electrons, which is the highest. It's the first one. And so there are two electrons there. And so what we're going to do is put a pair of electrons like that to indicate the two electrons in the first energy level. Now, is it paramagnetic or diamagnetic? So recall that you have an element that is diamagnetic if all of the orbitals that are occupied by electrons have a pair of electrons in each of the orbitals that are occupied by electrons. And so here we have a single orbital that's occupied by electrons, and there's a pair here. So this must be diamagnetic. Okay, now another thing I want to kind of briefly digress and talk about, which is very important, is you should know that helium is very stable. It is very stable and has low potential energy, and therefore it's unreactive. And so helium atoms tend not to react with any other elemental atoms, and they don't react with other atoms of themselves. And so you already know one reason that this is true is because helium is a noble gas. But there's actually a more important reason now which you can understand. So you will have a very stable, low energy, potentially very unreactive element if the highest energy level that has electrons is filled with electrons. And so what you can see is that the highest energy level here is the first energy level. There's only a 1s orbital in the first energy level. There are no p or d orbitals, so there's only one orbital to fill in the first energy level, but it is filled with electrons. And so the highest energy level is filled with electrons. And then when you fill up an energy level with electrons, that makes the element very stable. And so that's why helium is stable. Okay, so we're going to move on to lithium. And there are 3 electrons in it. So let me just do the orbital notation for this. And so there are 2 electrons in the 1s orbital. The third electron goes into the next orbital up in energy, which is the 2s. So that is the correct configuration. And so what is electron configuration notation? It's 1s2, 2s1. How about the quantum numbers? Well, this first electron here will have a set of quantum numbers which is 1, 0, 0, 1/2. This next one here is going to be 1, 0, 0, negative 1/2. How about this one here, this one electron in the 2s? What will its quantum numbers be? So you can see now we have an electron in the next energy level up in terms of energy, which is the second. So N is the energy level, so N must be 2. So for this electron here, its quantum numbers are N is 2. It's still here in the second energy level, electron is going into a 2s orbital. And so an s orbital or s sublevel has a value of L that is 0, that is always set. Therefore, it has a value of m sub L, which is 0, because there's only one s orbital. And if it's 0 in L, it must be 0 for m sub L. M sub s, it looks like it's an electron pointing upwards in this diagram, so it's spinning clockwise, and so it's going to be plus 1/2. So these are the quantum numbers for this electron here. So a lot of times people put in brackets around the 4 quantum numbers, and you're welcome to do that, and I've done that there. Okay, so what is the Lewis dot structure for lithium? So lithium has now a total of 3 electrons. But remember, when you are writing out a Lewis dot symbol for an element, you only consider the electrons in the highest energy level. So lithium, although it has 3 electrons, they're going into 2 energy levels. The highest energy level is the second energy level, and there's only 1 electron there. So again, with the Lewis dot structure, we only consider the number of electrons in the highest energy level. There's only 1 there. So lithium only has 1 dot. Now, is it paramagnetic or diamagnetic? Well, here is a situation where we do have an orbital that has only 1 electron in it. And so that would allow that element, lithium, to be attracted to magnetic fields. So it should be paramagnetic. Okay, the next one is beryllium. And there are 4 electrons here. And so the 2 orbitals that are filled up are the 1s and 2s, like this. And so the electron configuration is 1s2, 2s2. I'm hoping you can figure out the quantum numbers for each of these 4 electrons of beryllium on your own, so I'm going to skip that. So what is the Lewis dot structure for beryllium? And so again, we consider only the number of electrons in the highest energy level, which is the second, and there are 2 electrons there. So I'm going to write beryllium here. Now with helium, there are 2 electrons in the highest energy level. I kind of put them together to sort of remind myself that helium is a stable atom. But with beryllium, that is not quite the case because there are empty 2p orbitals here that are not filled. So this is not as stable as helium. So to indicate that there are 2 electrons in the highest energy level, but it's a relatively unstable atom, I'm going to put 2 electrons there like that. Okay, so is it paramagnetic or diamagnetic? And you can see that all the orbitals with electrons in them have a pair of electrons, so it should be diamagnetic. Okay, so the next one is boron, 5 electrons. What is its configuration? So 1s is filled, 2s is filled, and then 2p are the next orbitals up in energy that get filled, and you just put 1 electron here in one of the p orbitals, and by convention we fill up this first line with an electron. Can you write out the quantum numbers for this electron? Well, what that would be, I'll put in brackets here. We have here for this electron, it's in the second energy level. It's in a p sub level. It's no longer an s sub level. This one is in a p sub level. So L now is equal to 1. Now, what about m sub L? So recall that m sub L can have values from +1 to 0 to -1 because L is 1. And so you have values from -L to 0 to +L. So it's -1, 0 to +1. So you might say, well, okay, this is the first one. So maybe -1. You actually can pick any one you want. You can write in -1 or 0 or +1. It doesn't matter which one you choose. It will matter if maybe you have multiple electrons here and you're trying to distinguish them in the 2p sublevel. But if you only have 1, it really doesn't matter. So I'll just pick one. So I'll just say -1. It looks like it's spinning clockwise, and so I'm going to put +1/2. Okay, so what is the the Lewis dot notation Well, again, it's going to be the symbol with the number of electrons on the highest energy level. And so there are 3 there, it would look like that. And it looks like it's paramagnetic. Okay, so the next one is carbon. And this has 6 electrons. This is a little bit trickier. So you have 1s, 2s, and then you have 2p. Okay, so there's 6 electrons. So the first 2 go into 1s, first 2 go into 2s. Now the 2p. So the first electron goes here, but where does the next final electron on carbon go? Does it go pair up with this electron here, or does it go into the next orbital there? Well, there's a rule called Hund's rule, which says is that if you have multiple orbitals that are degenerate, meaning they have exactly the same energy, you put 1 electron in each orbital before you put a pair in 1 orbital. So what we're going to do is if we have 2 electrons that go into 2p, because of Hund's rule, we must put this electron here in one of the other 2p orbitals, because again, the 2p orbitals have the same energy, they're degenerate. Okay, so I'm going to skip the quantum numbers, but I'm hoping you can figure those out if you wanted to. And then I'll write the Lewis dot structure here. And then it looks like this will be paramagnetic. Okay. What I'm going to do now is we're going to skip nitrogen and move on. So I'm going to give myself some space here. I'll keep some of these down here maybe. Maybe I'll keep carbon. Okay. So we have N, L. So we're going to skip nitrogen, which has 7 electrons. Let's go on to oxygen, which is 8 electrons. So orbital notation, 1s, 2s, 2p is next filled. There are 8 electrons, so 2 go in the 1s orbital, 2 go in the 2s orbital. And then this is the 5th one, the 6th one, and we put the 7th one here because of Hund's rule. And then the 8th one, now you can have a pair in one of the orbitals. And by convention, we put it on the first of these orbitals of the ones that are degenerate. So that is the orbital notation for oxygen. So what is electron configuration notation? It is 1s2, 2s2. It looks like we have 5 electrons in the p sublevel, so it's 2p5. How about quantum numbers? Let's just take this 1 electron here and see if we can figure out quantum numbers for that. Okay, so this electron here will have a set of 4 quantum numbers, which should be different than all the quantum numbers of these other electrons. And so it looks like it's in the 2nd energy level, so n is equal to 2. L is going to be equal to 1 because it's the p sublevel. M sub L, well, your choice is either 1, 0, or -1. So if I had, for example, m sub L of this electron pointing up here, and this orbital would be +1, and I had this one set to be 0, then I would set this one to -1. So I can set this one to -1 knowing that these other 2 electrons in the 2p sublevel need to have a different value of m sub L. And so here the electron is pointing up, and so it has a clockwise spin, so it's +1/2. Okay, so what is the Lewis dot structure for oxygen? So you're looking at the symbol here for oxygen, and so it'll have as many dots as electrons in the highest energy level. And so it looks like we have what? The highest energy level, be careful here, a little bit more difficult to see. We want the highest numerically, highest number energy level. So 2p is a higher energy sublevel than 2s, but they're both part of the 2nd energy level. And so we're considering energy level here for highest energy level electrons. So the 2s, 2p, these are the highest energy level electrons. So there's 2, 4, 5, 6. So it needs 6 dots. So I'm going to draw a pair here, and then 5, 6. And this looks like it's going to be paramagnetic. Okay, so next we're going to do fluorine. I'm going to just erase this to give me a little bit more room. Okay, so fluorine is 9 electrons. So this is 1s, 2s, 2p, 2 electrons here, 2 electrons here, 5, 6, 7, 8, 9. Okay, so that's the orbital configuration for fluorine. Electron configuration notation is 1s2, 2s2, 2p5. How many electrons does fluorine have in its numerically highest energy level? It's all the electrons in the 2p and the 2s. So it looks like there's 2, 4, 6, 7. So fluorine should have this Lewis dot structure. And this is paramagnetic. Okay, how about neon? So this has 10 electrons. So its configuration is 1s, 2s, 2p. And I think what you can sort of see here is we have enough orbitals written out at this point. There are a total of 6 of them. Wait, excuse me, 5 of them. I can't count. There are 5 orbitals here, each accepting a pair of electrons for a total of 10 electrons. And so its electron configuration is 1s2, 2s2, 2p6. And so we have neon. And so now we have 8 electrons in the numerically highest energy level. So it's 1, 2, 3, 4, 5, 6, 7, 8. And so this is going to be diagnetic. Okay, so I want to talk a little bit about neon now. Okay, so neon is also very stable. So I'm going to draw a box around it like this. This is very stable. And it has low potential energy and very unreactive. Okay. So the reason why helium was stable is because its highest energy level, which was the first energy level, only had 1 orbital, and you only needed 2 electrons to fill it, so it was pretty easy to fill an energy level. So neon is probably even a little more stable than hydrogen, and the reason is there's a couple reasons. So one thing you'll notice is now at this point we have completely filled up the second energy level, which was comprised of the S sublevel and the P sublevel, with electrons. So the second energy level is completely filled with electrons along with the first. So all energy levels in this element are filled, so that makes it stable. But it's stable for another reason. If you have an electron configuration that has 8 highest energy level electrons, then that is called an octet, and that gives it further stability. And so here what you can see is this highest energy level is second. It has 8 electrons in it, as indicated by the Lewis dot symbol. There are 8 electrons here as around the symbol. So therefore, if you have an element with an octet of electrons, because there are 8 electrons in its highest energy level, then that makes it very stable. And again, if it's very stable, it's going to have relatively low potential energy, and it won't want to react with other atoms of different elements, nor of atoms of itself. Okay, so let's do a few more and then talk a little bit about this. Okay, so I'm going to erase carbon. So I'm going to put on sodium, so you can see that this just continues on and on. And so you'll have the 1s, 2s, 2p. Do you remember what the orbital next that is filled? It's 3s. So here I'm just filling up the first and second energy level with electrons. And so sodium has 11 electrons, and so the 11th electron goes into 3s. So can you write out a Lewis dot structure for sodium? So the question is, does it have 9 electrons? And the answer for the Lewis dot structure, and the answer is no. It only has 1 electron, 1 dot. And the reason is, again, you'll have as many dots as electrons in the highest energy level. Numerically, the highest energy level now is the third. There's only 1 electron there, so it should have 1 dot. Is this paramagnetic or diamagnetic? And so we have a single orbital here with 1 electron, so that makes it paramagnetic. Okay. Now, there's something that's kind of important for you to know at this point in time. This is one of the most important things that you can learn about chemistry. Okay, so here with neon, we have an atom with 10 electrons, and that was exactly enough to fill up the first and second energy levels. And all the orbitals in the first and second energy levels are full of electrons. There's no more than that. There's no less than that. That makes the atom very stable. Other atoms will not have that electron configuration. They'll have maybe more electrons than that, obviously, or they'll have less. Now, what an atom will want to do is it will either want to lose electrons or gain electrons such that it can become a configuration where all its energy levels are full of electrons. So look at sodium here, and we have 11 electrons. You can see that these lower energy levels are filled with electrons. We have the 3s energy level has 1 electron. What sodium can do is it can do this. If it can lose its 3s electron, if it goes somewhere, guess what kind of electron configuration it now has? So now sodium was 11 electrons, but now it's down to 10 electrons. And so it would have a positive charge in this example. When it has lost that electron, look what has happened. Now the sodium ion does have neon's electron configuration, so it's very stable. So by losing 1 electron, it achieves a noble gas, neon's a noble gas, a noble gas filled energy level configuration, and it becomes very stable. Now, is it what we saw with sodium in this example, that it could just lose 1 electron to get that noble gas neon configuration? Is it possible for elements to want to gain electrons to do the same thing, get a noble gas configuration? And the answer is yes. So we have fluorine here, and you can see that fluorine's electron configuration with its 9 electrons is 1 away from neon's stable configuration. So if it can get an extra electron here, it goes there. And so now, before you had fluorine with 9 electrons, I just added 1. And so now it will be fluorine with 10 electrons. I'll put a negative charge here. So this 9 would be changing to 10 electrons. And so now you can see that fluorine with an extra electron now has a noble gas configuration. So now you can sort of see why sodium tends to want to lose an electron and fluorine wants to gain an electron, and why you can form a compound between elemental sodium and elemental chlorine. So what will happen is when you form a compound between elemental sodium and chlorine, they probably will not want to stick together on their own because sodium has 11 electrons and fluorine has 9 electrons. But if sodium loses its 1 electron in its highest energy level, it goes down to 10 electrons and it becomes positively charged. That electron can be transferred to fluorine. It goes from 9 electrons up to 10 electrons and it becomes negatively charged. So when you have a transfer here of electron from sodium to fluorine, both elements achieve a noble gas configuration and those ions become very stable, and because the ions are oppositely charged, they bind together. So for example, with magnesium, you could write out the configuration. And so you might recall that magnesium the ion has a 2+ charge. Well, magnesium has 12 electrons. I'm not going to write all this out, but what you would find is in the 3s sublevel, there are 2 electrons here in its configuration. So maybe now you can sort of see why magnesium ion is +2, because if these 2 electrons leave, then these lower energy levels are left in magnesium ion and they're filled with electrons. And so it tends to want to lose 2 electrons. Okay, so I want to do a few more examples. And now we're getting into odd electron configurations. Okay, so let's do vanadium. So we have vanadium, which has 23 electrons. So that's a lot of electrons. And so you can work it out, but you will find that the 1s orbital is filled, the 2s orbital is filled, and then the 2p is next, 3s, and then 3p, and then we have the 4s, and then I need a little bit more room here, so I'm going to write 3d. Okay, so we don't need this chart anymore. Okay, there we go. Okay, so it has 23 electrons, and so 4, 6, 8, 10, 12, 14, 16, 18, 20, and then 21 goes here, and so you might ask, where's the 22nd electron goes? Well, remember that these 5 orbitals here in the d sublevel have exactly the same energy. They're degenerate orbitals, and so Hund's rule applies, and so we put the 22nd electron here, and then the 23rd electron goes here. So this is a correct configuration for vanadium. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So that's pretty cool, right? Or maybe that's not the right word, but that is correct. Okay, so now we're going to go try the next element up, which is chromium. It has 24 electrons, but it's not going to have the configuration that you would expect. So I need to talk a little bit about that. So chromium has 24 electrons, and so the 1s are filled, 2s, 2p, 3s, 3p, and then just for, well, I'll put 4s here is fine. And then I'll put 3d here. And I'll just draw lines here for electrons to speed this up a little bit. Yeah, okay, so here are the electrons filling the 3p. Okay, now we have an extra electron more than vanadium. So what you would think is that there would be 2 electrons in 4s, and then vanadium with 23 electrons had 3 in the 3d, and so you would expect chromium with an extra electron to have 4 in the 3d. So you might expect this. Okay, and so this is a reasonable expectation. The problem is, experimentally, we have found that chromium does not have this configuration. Instead, it has something a little bit different. And what it has is as follows. What it has is what we have found experimentally. If you look at the 4s sublevel of chromium, it only has 1 electron there. And this electron here is moved down to fill this orbital, the 3d sublevel. So this is actually what I'm writing now is the correct configuration of chromium. 1 electron has left the 4s, and it's gone down to fill the 3d. So chromium still has 24 electrons. They're just not quite in the places where you would expect. So it's 1s2, which is normal, 2s2, 2p6, 3s2, 3p6. This is all like before. And now chromium has 1 electron in the 4s, and it's pushed that other electron in the 3d. So it's 3d5. So why did it do that? And what we think is going on is that if you have a configuration that only needs a single electron to completely fill the sublevel, it will take an electron from a slightly lower energy level. So the 3D sublevel has a little bit higher in energy. The 4s sublevel is a little bit lower in energy. But what will happen is because we had 4 electrons to start, we can just go ahead and grab an electron for 4s and stick into the 3D, and now we have completed the 3D sublevel. And when that happens, that lowers the energy of the 3D sublevel even further, even less than 4s. So if you have a half-filled sublevel, or in other words, 5 orbitals, each with an electron, that stabilizes the sublevel even lower to make it lower energy than 4s. Okay, let's do another one, copper. So copper is 29 electrons, and so it's kind of the same deal. So it's 1s, 2s, 2p, I'm getting messy here, 3s, 3p, and then 4s, and then 3d, so 1, 2, 3, 4, 5, 3d. So copper is 29 electrons, so the 1s is filled, 2s is filled, the 2p is completely filled, 3s is filled, 3p is filled. And then how about the remaining sublevels? So normally you would think it would be this. And you can see with 29 electrons, this is what you might expect. But again, experimentally, we don't find that. Instead, what we find for copper, we only have one electron in the 4s sublevel, and we have now a full 3d sublevel for the same reasons as chromium, in that if you move an electron from the 4s sublevel and now fully fill the 3d sublevel, that imparts extra stability to it, and now the 3d sublevel has lower energy than the 4s, and so that will be filled first. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it's, or excuse me, I made a mistake. It's 4s1. Oops, don't make the mistake I did. Okay, and it's 3d10. Okay, so what I want to do, well, I see that you can't see that. I'll write it up here. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. This is for copper. Okay, and so this will have 29 electrons. Okay, so let's move on. Okay, so there are a couple other things here that I want to kind of mention about these irregular electron configurations. And so the ones I just went over were chromium and copper. So this is the normal configuration, or what you would expect for chromium, but it's not right. And this is the true configuration of chromium, which I went on over the board. Here is copper's configuration that you might expect, but it's wrong. This is the true configuration. And here are some examples of other elements where you have new configurations that you don't expect. And so the basic rule to remember is that if you have, say, a d sublevel that is one electron away from being either half filled or fully filled, it will take an electron out of the lower s sublevel and fill up the d sublevel. So for example, you can see with molybdenum, it has a lot of electrons, I forget the number, but in the outer shell there are 2 electrons, and you would expect 2 electrons in 5s and 4 electrons in 4d. But you can see it's 1 electron away from being a half-filled sublevel, and so 1 electron is taken away out of the 4s. So this is not correct, excuse me, out of the 5s. And so that electron leaves the 5s and goes into the 4d, and so now the 4d sublevel with 5 electrons is half-filled. So you also have weird ones like ruthenium, and so here 1 electron from the 5s is removed to go into the 4d, but it doesn't even half-fill it. It still happens. You don't have to remember that one. That's unusual. The only ones you really have to know are the ones where all you need to do is take out 1 electron from a lower energy s sublevel, and if you add it to the d sublevel, it will either completely fill it with 10 electrons or half fill it with 5 electrons. That's the only thing you'll need to know. And we'll probably go over this on some worksheets. Okay, moving on. Okay, so what I've been doing in this sort of presentation is talking about a little bit about the differences between electrons in the highest energy level versus electrons in lower energy levels. So the name of electrons in the highest energy level is called valence electrons. And so here, if I got sort of a picture of it here, and so because valence electrons are electrons in the highest energy level, they can be found the furthest out from the atom, while the electrons in the lower energy levels are called core electrons, and they're further into the atom. And so one of the things you may have heard maybe from a previous chemistry course is that if you have an atom react, it's usually that atom's valence electrons that are either be transferred to another atom or are being shared with another atom. And you can sort of see why. You would not expect the core electrons to either leave the atom or be shared with another atom because they're further down. But the valence electrons are on the outside of the atom, and so they're far more likely to either be lost by an atom to go to another one or to be shared. Okay, moving on. So you should be able to identify valence electrons and core electrons. So here we have chlorine's electron configuration, and you can see that there are 3 energy levels here. There's a first energy level with electrons, a second energy level, and a third energy level. And so if you were to be asked what are the number of core and valence electrons in chlorine, could you answer the question? So here, if we want to identify the valence electrons, we just look for the electrons in numerically the highest energy level, which is the third. So these are the valence electrons here. And for the core electrons, we look for the electrons in the lower energy levels, the first and second. So these are the core electrons here. So it looks like chlorine, how many total valence electrons it has? It's in the any electron in the third energy level, there's 2 in the S sublevel, and there's 5 in the P sublevel. So chlorine should have a total of 7 valence electrons. And so I think I've indicated that there. So you can sort of see here, this is another representation for the configuration of chlorine, which we'll go over. But yeah, it looks like these are the valence electrons, and there are 7 of them. How about calcium? So I'm hoping you can sort of look at this picture and see that calcium has only 2 valence electrons, which are in the 4th energy level. And then it looks like it has how many core electrons? Let's see, it's going to be 2 here, another 2 for 4, another 6 for 10, and then another 8 for 18. So calcium looks like it has 2 valence electrons and 18 core electrons. Okay, so the last thing I want to go over is something very important in chemistry. So you're now at a point in time where you can really understand why is it that elements in the same column have the similar properties. And so why would elements have similar properties? So that's a good question to ask yourself. And so what would be the requirements for elements having similar properties? Well, one thing you would want to look at is the ability of an element to react with other kinds of atoms. And so what you may note is that certain elements react with particular kinds of atoms that other elements do not react with. So you see what these similar elements may have in common to react with this particular group of atoms. And so if you look at, for example, the halogens, you probably know already that the halogens, which are fluorine, chlorine, bromine, and iodine, have similar properties. And so now you can understand why. And the basic reason is because all these elements have the same disposition of electrons in their highest energy levels, meaning they have also the same number of electrons in their highest energy levels, so that they have similar reactivities. So let's go over this example in particular. So with fluorine, the highest energy level electrons are in the second energy level, and there are a total of 7 highest energy level electrons, the 7 valence electrons. So let's look at chlorine. If you look at chlorine's configuration, it also has 7 highest energy level electrons, 7 valence electrons. It's just that they're in the next energy level up. They're not in the second energy level, they're in the third energy level. Bromine has 7 highest energy level electrons now in the 4th energy level, so it also has 7 valence electrons. And iodine now has those 7 highest energy level electrons in the 5th energy level. So it also has 7 valence electrons. So all these atoms here have different number of electrons. It's just that it has exactly the same number of electrons on the very outside of each of these atoms. And so because of that, they have the same number of electrons on the outside. They're going to react in the same way with other elements. So that is why they have similar properties. So thank you for listening to all that, and we'll see you next time.